atingir os capitais quânticos, né? Japoneses e russos.
There is at least one person. I asked Kaivan to be where I usually teach, and anyone who would come here. Yeah.
Okay.
Aqui tá bom. A gente vai sentar no jatinho.
Aqui as pessoas estão citando para destaque dos sistemas. A gente fazer destaque.
Ok. Podemos iniciar. Primeiro, coisa legal, esse seminário vai ser gravado, vai ser no canal do YouTube da AMP. Se você faz qualquer pergunta, se você faz qualquer pergunta, você dá permissão para ser parte da gravação. Hoje estamos abrindo a sessão do seminário. Temos um prazer de ter o Felix Kling. Ele é da Alemanha, fiz mestrado em Heidelberg e depois fiz doutorado na Universidade de Arizona. Quem outro que fez doutorado na Universidade de Arizona? Só para dizer. Na verdade, a coisa engraçada... Yeah, of course. Na verdade, a orientadora dele foi Chufa Mitsu, que é parte do concurso na Universidade de Arizona, foi de almoçar com o comitê de estudantes de doutorado no tempo. Eu lembro dela a causa disso. Isso é trabalhar em fenomenologia. Depois ele fez doutorado, depois ele fez pós-docs na Universidade de Irvine, no SLAC, e lá ele decidiu de ir para coisas um pouco mais experimentais, mas também com fenomenologia, e agora ele está no DESE, é coordenador científico do FASER, que é um experimento, não é arma do Star Trek. Ele vai falar um pouco sobre as perspectivas do físico do FASER. You can start?
Okay.
Yeah.
Okay, eu não falo português, eu preciso falar inglês. Okay, so I just speak English now, sorry. Yeah, thank you for the invitation. It's a very nice introduction. So I will talk about the FASER experiment and the exciting physics that we can do with it. I wanted to first see who the audience is. So who considers themselves more of a theorist? And okay, and who is more of an experimentalist? Okay, so let's say half-half, maybe a little bit more experimentalist. Okay, good. I will try to have both. Who is more interested in new physics searches, dark matter, something like this? Okay, like maybe a third of the room. Who cares more about standard model, neutrinos, astro-particle physics? Okay, so the other half of the room. Great. I think you will all be happy. I have a mixture of everything. Okay, so FASER is an experiment. It's an existing experiment. As you can see, it's right here. And it's at the LHC. So this here is the LHC. And I'll first tell you what it's doing and why it's there. And then you see the big picture. And then I show more details and pretty pictures. Okay, so the main focus of the LHC, as you probably all know, is to measure, discover, see new heavy particles, so like the Higgs boson that we have seen, or supersymmetric particles that we have not seen. And its main experiments, Atlas CMS, were really built, designed to see them. So you have the protons colliding, producing these particles that decay roughly isotropically. So you build giant detectors around that really cover most of the cover the full solid angle. to catch its decay products. However, and this was, of course, very successful. Someone won the Nobel Prize with world-leading limits of measurements of the Higgs boson, limits on supersymmetry. And the question I asked myself as phenomenologist this year is what else can we do to maximally exploit the LHC? And what I looked at was the forward region. So this is typically ignored by most standard LHC physicists for two reasons. Well, it's not covered by the main experiments because there are holes in the front and the back to let the beam in and out. So it's simply not equipped. So we can't really measure anything yet. It's also the stuff that's produced there is mainly pions and kaons, so light standard model particles that we already thought we understand very well. So this wasn't really the main region to look for interesting new heavy physics that we mainly want to probe at the LHC. However, we really get a huge amount of, I think I went one step too far, a huge amount of these hadrons in the forward direction. Something like 10 to the 17 pions, 10 to the 13 beam mesons within 1 milliradian of the beam. So that's roughly the size of the moon on the sky. That's a huge fraction of the mesons produced, and they typically have all the TeV-ish energies. So they are formed by the remnants of the colliding beams. So the beam energy has to go somewhere. That's what it goes into. So what can we do, or can we do something interesting with a huge amount of very energetic hadrons? Well, the answer is obviously yes. Otherwise, I wouldn't have been invited to speak here about it. So these particles can decay, for example, in neutrinos. So we can get a beam of TeV energy neutrinos that is strongly collimated and rather intense in the forward direction. Or they can decay into other light weakly interacting particles that we have not observed yet. Name your favorite example: dark photons, axion-like particles, there are neutrinos, dark matter, something like this, that are light enough so that they can be produced there too, and that also at TeV energies. And these particles, they would essentially form a strongly collimated beam along the tangent line of the ATLAS experiment and just go straight. So how could we see them? Well, we can't really put the detector right here because that's where the proton beam is and we can't block it. Also, it's like super radiated environment. Detector components don't really like that. But so they go down the beam pipe undetected. But then the LHC is roughly a ring, right? So eventually it will curve away. And the beam will continue going through some rock. And our idea was to place a detector roughly there where I put it and catch them a couple 100 meters away. So this is the main idea of the experiment. So we called it the forward search experiment. Let's see. No, let's go back. Well, the forward search experiment that's designed to catch these particles, both neutrinos and decaying new other particles. Okay, so this is, let me first talk a bit about the experimental program that came out of the idea. The idea was conceived by 4 theorists. It was, as you imagine theorists to work. We drink a coffee after lunch and draw random things on whiteboards, and then magical ideas emerge. That was one of those examples. So then in the next step, we looked at, okay, could we actually place this experiment we imagined somewhere? And so we looked at a map like this. So this is CERN's version of Google Map. Here you see Atlas. This one here, the slightly curved one, is the LHC ring. This one is the SPS ring. Here, the red dashed line, this is the beam collision axis, so where the neutrino beam would go. And if you look carefully, it goes through a tunnel here. So this was an auto-injector tunnel during lap times. It's not used for the LHC. They built a bigger injector tunnel. So it's a conveniently located, unused tunnel. So that's where we thought we could put it. And I just skip ahead a few years. And actually, 2 experiments were to exploit that. The FASER experiment that I've been working in, and the other side is a SND at LHC detector, the scattering neutrino detector, which basically also liked our ideas and decided to do the same thing on the other side. So we have two detectors now, two neutrino detectors to exploit this. Okay, how would the experiment work? So this is my theorist PowerPoint version of how it works. So our original idea was to look for new physics, so for decaying new particles like a dark photon. So this is, I mean, we have long-lived particles in the standard model. Pions and kaons are great examples of it. So why not in the new physics particles that are long-lived? So dark photon is one example. It would decay into an electron pair. It would be highly energetic. You remember I said these particles all have TeV energies. So the signature would be that there is a energetic pair of electrons emerging in an empty decay volume, pointing back towards the Atlas collision point, a couple hundred meters, about 500 meters away from Atlas, after like a roughly 100-meter deep fall. Okay, so that's something that you don't expect to happen in the standard model. And to see that, we thought that, oh, well, you should have a sort of tracking system to see that there are two tracks, a magnet to split them and measure their momentum, calorimeter to measure their energy, and some front vectors to make sure that nothing undetected came in, like a muon or something like this. Okay, so this was our theory idea, and then later we also thought about neutrinos. First, we thought about it as a background. It's not really a background. Neutrinos don't produce electron pairs, but they're an interesting signal on its own. So we put an additional neutrino detector in front that's really designed to see the neutrino interaction, so nothing comes in, stuff comes out, and really measure them with high precision. Okay, so that's my theory PowerPoint version of it. Oops. This is a more sophisticated technical drawing by the experimentalist. And if you look carefully, it's pretty much the same things, just more professional looking. So the particles now come from this side. So here's a neutrino detector. There are 3 magnets with tracking systems in between, donated by Atlas. Many thanks to Atlas. There are some scintillating system everywhere to make sure that we can see these particles, trigger on them, and then a calorimeter at the end, donated by LHCb. So ended up being really cheap because we used a lot of spare parts of other much bigger experiments. This is how it looks like. So basically the same, just with much more cables sticking out so that you can barely see anything else. We built a trench. So this was a side tunnel, the one that you saw on my opening slide. That was on the side of the LHC. And we built a trench to really or align it with the beam collision axis, so this goes right through the middle of the detector. Okay, good. We also, I just mentioned it briefly, but for some of you who might have heard it, we have the idea of, since we have these detectors now, of extending the program and building bigger detectors in the given infrastructure. So here is a bit tricky because there's rather limited space in these tunnels that were built in the early 80s. We would like to have bigger detectors, and our idea is to create a dedicated forward physics facility, so new cavern a little bit further down here, still on CERN land, that's really built around the needs of the experiments. So not try to squeeze experiments in all tunnels, but build a new one that's built around the experiments. And actually, it turns out to be cheaper than trying to extend the old tunnels from the 80s. So this got quite some momentum, and a lot of effort from the CERN teams went into to plan this, and this would greatly enhance the physics potential, as I'll show in a moment, for BSM searches, but also neutrino physics with implications for QCD and astro-particle physics. If you want some more details, I mean, I shared the slides with him. I'm not sure if they will be uploaded somewhere, but there are a bunch of links of papers, white papers, workshops with more details in case anyone is interested. Okay, so let's go into what physics we can do. I start with a light new physics, and afterwards I go to the neutrinos. So maybe as motivation, so we know there's a standard model. We are made of it, and we have measured it in great detail at various particle physics experiments. That's this side. We're also pretty sure that there is some sort of dark matter sector that we know from astrophysical observation, rotation curves, CMB, bullet clusters, and so on. And what we would like to understand is, what is this dark sector? And is it connected to our visible sector? Why is there as much dark matter as we observe? Well, one thing, I mean, as a theorist, I want to answer these questions and to answer them mathematically, or to make any predictions, we need to make some assumptions on what is this dark matter. And to calculate the abundance of dark matter, what one typically assumes is that there is some sort of interaction between the dark matter and the visible sector. So for example, that they were in thermal equilibrium in the early universe, and then dark matter throws out. But this really requires a mediator. Okay, so this is our simplified picture. We have some dark matter, some mediator in the standard model sector. But what could this be? So about 10, 15 years ago, everyone really liked the WIMP, the weakly interacting massive particle that was coupled to the visible sector through, let's say, the Z or the Higgs boson. So this could be a neutralino in SUSY, for example, very popular at the time. But the problem is you can't make the dark matter as light as you want. So if Audie Lee and Weinberg in 77 said that if we make it lighter than about a GeV, we necessarily end up with too much dark matter. Actually, we can make it a little bit stronger now with the invisible decay response from the Z and the Higgs. So what this means is to make a light dark matter model, we necessarily need a new mediator besides the Z and Higgs boson. So some new portal, something like this. This is a dark photon. So we imagine that there is a sort of photon in the dark sector. Not too surprising. There's one in the visible sector. Why not in the dark? And that could kinetically mix with our standard model photon. So in the Lagrangian point of view, we would write down an operator like this here. So our field strength and the dark photon field strength with some coupling in front. That's called epsilon, like everything in mass that you see, that's called epsilon. This should be rather tiny. So our dark and visible sector can couple with this. There are also other ideas like a dark Higgs boson or a stellar neutrino or an axion that could serve as a portal, but let's just focus on this dark photon. Okay, so just to go in more detail, so the dark photon, which will be my example of light new physics, can arise in many hidden dark sector models. It's a gauge boson, a U1 gauge boson of some hidden gauge group. Can be massive. My example will be massive. And it's weakly coupled to the standard model via this so-called kinetic mixing. So it can just mix with a standard model photon. And if you rotate the basis a bit, what it results in is that essentially it couples to the fermions, to the charged fermions, with this coupling that's like the one of the photon, but suppressed by a factor epsilon. So it has a very small coupling to charged particles. What is the phenomenology of this particle? Well, it's essentially produced in any process that produces photons, as long as kinematically allowed. So for example, at the LHC, photons are mainly produced in the decays of pions. So pions decay to 2 photons. Now it could decay to a photon and a dark photon, with a branching fraction that's roughly speaking 2 times epsilon times the phase space factor. So this can actually be very large. If you make this to be, let's say, 10 to the minus 5, so epsilon is 10 to the minus 5, you have a branching fraction of 10 to the minus 10. Small enough to await a lot of bounds, but we had 10 to the 17 pions. That means we would still produce 10 to the 7 dark photons. So the LHC could be a dark photon factory without us knowing. But also, the same coupling controls its decay, so it could decay. And here I assume that it can't decay to dark matter. I just make the dark matter slightly heavy enough. So then the decay risk is proportional to epsilon. So the lifetime, so it has a small decay risk, so long lifetime. So it actually can be long-lived. In this case, it's for this benchmark here, it's about 100 meters, and it would mainly decay to electrons. Okay, how does it look like? So this is the landscape of the dark photon. Here's the mass, here's the coupling. We have some, let's see, can I, yeah, here. here are some bounds from like resonance searches. Here are some bounds for like displaced particle searches, so long-lived particle searches in gray. And shown in red is sensitivity we expect to see at FASER. So we sort of approach this open area in between here from the bottom end and can start to close this gap. What's interesting here is I started this discussion with dark matter. So here is a so-called relic target line. So this combination of parameters would explain the observed abundance of dark matter. And we can see it goes right through this region. Of course, I've conveniently chosen the parameters of the model such that this is the case. But actually, if you vary this a bit, it's like plus minus an order of magnitude around this line. You can't move it down infinitely much. So it's actually a rather somewhat generic prediction. Let's say it this way. Okay. So we can actually probe a nice region of the relic target space, and keep in mind that everything that's below the line is technically excluded because there would be too much dark matter in the first place. So that can't be true. Okay, so let's see what we did. So at FASER, we actually searched for this particle. So it would this was our very first analysis. So was really optimized for robustness and discovery. I mean, well, our first analysis, so we really wanted to make sure that we don't mess it up. So we were like very, very conservative. And we essentially looked for events that where something collided, nothing came in to the detector. So there were collisions at Atlas, nothing came in the front vectors. And then we start to see a signal that's consistent with two charged tracks in both the scintillators at the spectrometer. And then some sizable energy deposit. And we expect to have 2 times 10 to the minus 3 background events. These are neutrinos that interact in some material in between that might randomly look like this. So maybe a neutrino interacting here could be a background. Turned out to be not something we expect to see. And then we looked at the data, and unfortunately, we didn't find anything. Well, otherwise, you might have heard about it in some popular news. But we could put a limit on this model, and that's shown by this slide here. So there are some new unexplored parameter space that has been constrained. Okay, so this is just one example of what one can do on the new physics searches. There are actually a large variety of models that have been considered in the literature, so with various motivations. So this is a sort of summary plot I once did that's nice and colorful. So particles of all quantum numbers introduced to solve all the big problems in the field, from dark matter, strong CP problem, inflation, neutrino mass generation, baryogenesis, or the hierarchy problems, maybe resolved by models of long-lived particles. And many of them can be probed at FASER. We also have another search. I don't want to talk about it, about axion-like particles decaying to photons. If you're interested, talk to me later or look at the backup slides. That can also constrain a variety of these models. Okay, and just to mention, in principle, in the forward direction, you can also look for a variety of other things. Like, for example, the dark photon could decay to dark matter, and then you would have a very intense, highly energetic TV energy dark matter beam that scatters in your detector. So this is great because direct detection experiments often suffer from, the dark matter being not fast enough or not energetic enough. This shouldn't be a problem here. We can look for milli-charged particles. So there is a dedicated experiment for MOSA that would look for this. One could look for quarks that have really interesting features, like they would move around in like these very weird trajectories. And this is an example of actually very heavy physics that could be probed there. Okay, if you're interested in that, maybe look it up or ask me later. But I want to go now to the second topic, and that's neutrino physics. So just to say, the idea is actually quite old, the general idea. It was first proposed by the Rujula in 1984, so this is 5 years before I was born, that there is actually a huge flux of neutrinos at what he called at that time future colliders. So this was a time when papers were still typewritten and equations were written by hand. So just to show that it's quite old idea. And nothing has happened for many decades until 2018, when actually the FASER collaboration has formed, and we put this tiny little detector in the side tunnel here. So this detector was like, well, maybe this big, like roughly like this box here. And we actually saw a couple of neutrino interactions in it. It was only there for like, was 10 kilogram, only there for like a couple of weeks, and all these some neutrino interaction candidates were reported. And that actually shows the potential of the forward direction, just because there is a strongly collimated neutrino beam directed in this direction. That's, of course, a great advantage. Okay, so we actually have now observed neutrinos with much higher significance. So the first analysis we did is, well, now with our full detector, was just to look for muon appearance. So roughly speaking, neutrino comes in, the front scintillator sees nothing, it interacts, and then the muon comes out. So you see that there is a track coming out. That's, you can measure its momentum. So the classical muon appearance search. So it only uses electronic detectors. That's great because they are really fast to read out. I will show on the next slide the emulsion detector and why it's much more complicated. So what could possibly fake the signal? Well, it could be muons that come from the sides, scatter a bit, and then also go this direction. There are some muons that make it to 100 meters of rock from Atlas, so this is something to think about. And actually, if we plot it, so here's the momentum of the muon, and here's, roughly speaking, the distance from the center. We see that there is a population of low energy muons close to the edge of the detector that we observe as expected. But then if you extrapolate in this region, here's our signal region. So muons that come from the central part of the detector and have high energy with no veto fired, we don't really expect to see anything there. So we estimated this. We expect like point something events from especially these large angle muons. These are the main issue. Also really hard to estimate. And then we unblinded this region and we saw, oh, there's a huge population of events that clearly has a different origin than those ones here that look exactly like our neutrinos should look like. So we have seen neutrinos, and if you do the math, that's actually, it's 153 neutrinos. That's a 16 sigma discovery. That's actually pretty high for discoveries. I mean, it's a point where 16 sigma becomes sort of meaningless statistically. So that's the first observation of collider neutrinos. And I will show you some later measurements, what we can actually do with it. We had another one. I mentioned a couple times our neutrino detector. So this neutrino detector, it's an emulsion detector, roughly 1 ton target mass, and it's tungsten plates interleaved with emulsion films. Emulsion films are photofilms. You probably know them from, well, actually, discovery of the Maya might be an example of it if you just look out of the front of the room. So rather historic, let's say, detection technique, but still used. Was used in Opera and Donut for neutrino experiments. We just used a small data set, like 10 inverse femtobarn, so that's like a weeks of running or something like this, only 100 kilograms. So it's roughly speaking 1% or so of the data we have collected so far, so really tiny fraction. The problem is it's photofilms, so you need to develop them, so go into a dark room, develop them with some chemicals, and bring them to Japan and scan them in some special lab, and then you have 700 films that all have a lot of dots that you need to connect. So it's really looking for the needle in the haystack. Our experts know how to do that. They have been doing that all their life, but it takes time. It's nothing that you can do just run a quick algorithm over your data. So you need to then also find the vortices, look for electron showers. So yeah, the showers in the data. I show an example on next slide, measure muon momentum and so on. But we found a couple of events. So we saw 2 electron neutrino and 8 muon neutrino events in agreement with expectation, each of them roughly 5 sigma significance. Here's the event I promised. So this is an electron neutrino event, I think a little bit above a TeV, 1.5 TeV or so. So this is from the side, so nothing comes in, and then you see a bunch of tracks coming out, rather collimated. If you look from the front view, so the neutrino sort of comes out of the wall, you see that you have an electromagnetic shower here recoiling a bunch of other particles, so that's the hadronic activity. And you really see a lot of details. You see that there is 11 tracks, so you can count them and learn something about the sort of substructure of the event. You can measure the energy here by just sort of track density. You can measure the momentum here via multiple Coulomb scattering. So really lots of information. It's super difficult to get the information, lots of effort, but once you have it, you really have a lot of information about the event. Okay, so now that we have seen neutrinos, and we actually have, as I said, like roughly 100 times more data than we have analyzed. So what do we want to do with it now? So again, we have seen them both with a muon appearance and with a dedicated emulsion detector. There was actually a nice media reportage about it. This is a YouTube video that shows, like, it's rather nice. That explains how this discovery was made. I really liked this article. This was by Elizabeth Worcester. I never met her. She's not a part of FASER, but she was asked to write this article, and she called it "The Dawn of Collider Neutrino Physics," which I think describes it rather nicely. So we are at the point of starting a new field of neutrino physics at colliders. Okay, so how many neutrinos do we expect to see? So this is for run 3 of the LHC, so that goes, roughly speaking, until the end of the year or mid of next year. So we expect to see 1,500 electron neutrinos, roughly 10,000 muon neutrinos, and a couple dozens of tau neutrinos. So this was a current experiment with the ones, so this are thousands of neutrinos. With a bigger FPF experiment, the forward physics facility, this would really be millions of neutrinos, explaining why we want bigger detectors to really go to precision physics. Also have then like 10,000s of tau neutrinos, that would really be tau neutrino precision physics. So what can we probe with them? Well, we can learn something about their production. So neutrinos come from, as you can kind of see, where do they come from? From pions. So muon neutrinos come from pions and from kaons. Electron neutrinos come from kaons and from charm. Tau neutrinos only come from charm. So we learned something about pion, kaon, and charm production. And those have not been measured before in the forward direction. So it's just something new that we haven't probed since, I think, the very first Hadron Collider, the ISR, in the 70s. Okay, so we can learn something about forward particle production, new complementary probe, but we can also learn something about the scattering. So it's the only beam we have of TeV energy neutrinos under controlled laboratory conditions. So we can measure cross sections or use them as a probe of nuclear structure. So this is a similar figure, just way more complicated. So let me very slowly walk you through. So this is a electron neutrino spectrum. This is a muon neutrino spectrum. So number of neutrinos interacting versus energy in like a bent histogram. And the different colors here is where they come from. So kaons, charm, and pions that we have already seen. And then the different lines is, different generators. And you don't need to know the generators. Let's just look at what the spread is. So for kaons, for example, it's roughly plus minus a factor 2. Okay, that's not too bad, but not too precise either. So, but yeah, getting experimental precision of a factor of 2, once you have like 50 events or so, you're better than that. And then charm is like plus minus, almost an order of magnitude. It's a little bit more spread than order of magnitude. Actually, a very bad prediction. I originally come from Higgs physics. There, people calculated at next to leading order at like % level precision. this is more than a factor 10 uncertainties. This might actually be the worst prediction of LHC physics we have made so far. When I first did the plot, I was rather disappointed because it's like, okay, we don't know. And then I asked, why do we not know? And I realized, oh, well, we can constrain all the things we don't know that go into these different predictions. And we can make progress early on. Like, we can really rule out these extreme scenarios, either here or here, with first data. It's like, it's a difference if you see like 10 or 100 events. That you will, with the first set of events you see, you will know the difference. So let's go to charm. That's maybe the easier one to understand. So this can be calculated using perturbative QCD. So you calculate Feynman diagrams. We all learned probably how to do that. At least we know where to look it up. And well, I asked several groups who did this to make a prediction. So either using hadronic interaction models, so Monte Carlo generators, or collinear factorization, or some people who like KT factorization, somewhat different formalism. And I asked them to make a prediction. And they made one first for LHCb, and they can, almost all of them can describe it rather well, sort of by construction. And I asked them to make a prediction for FASER. And well, as I show, like all these colorful predictions here are the ones from charm, and they really differ by quite a lot. So one very obvious statement that one can make is collider neutrinos will be able to distinguish predictions that LHCb alone cannot. Okay, why not? Or let me just show you one example of data. So this is for electron neutrinos, where pions and kaons are not so dominant. For muon neutrinos, they really dominate most of it. Actually, FASER data on muon neutrinos ruled out some of the models already. So this is personally my favorite. It's EPOS LHC for pions and kaons, and then some POWHEC plus PCI8 for charm production. And this is the predictions from the different fluxes and how they compare with data. Okay, we have a sort of deficit here in prediction. Most of the generators have, but otherwise it looks more or less okay. I mean, when I saw that the first time, I thought, this is great. I made a prediction, having absolutely no clue if I might be an order of magnitude off or not. And it's roughly right. So success as a theorist. Some of my colleagues, the one from the other experiments, they always really like to use this generator here. Well, the reason is because it gives them higher numbers. But if we compare it, we see that, well, it predicts way too many neutrinos from charm here, very high energy, that we know are just inconsistent with data now. Okay, the real reason why I didn't like this generator is because I asked the author, and the author told me, Felix, don't use it. I know it's wrong. Don't use it. So that's typically a bad sign. But now we also show with data that this is simply not a good generator. So we learned already something. So for example, that this generator is wrong. Okay, we kind of knew that before, but the problem here was that their charm quarks were massless, and that caused a lot of problems. Okay, but what goes in this calculation? Well, if you like perturbative QCDs, then okay, you have like PDF of the one, or it's gluon goes to charm, and you need to PDFs of the gluons times the hot matrix element. Hot matrix element we can calculate. That's not so tricky. What is the PDFs? Well, we want the neutrino to be very energetic, so we need TeV energies. So one of the momentum fractions should better be large. The momentum transfer, well, it's very forward. We don't want high PT, so this is typically at the threshold, so somewhere around like the charm mass. And then you can calculate what is the other momentum fraction. Well, it's 4mc squared over central mass energy, so 10 to the minus 6-ish. So if you look at the PDF landscape, momentum transfer versus momentum fraction, we have a high X gluon and a low X gluon. And you see that, oh, this is interesting. This is in a region where there is no other constraint by fixed target experiment, Hera, EIC, okay, that's not existing yet, Tevatron or LHC experiment. So we really probe a unique low X region. If you look at current PDF uncertainties, so this is the gluon PDF as a function of X, and the current constraint is this orange region here, so it's essentially completely unconstrained at low X. So what do we learn? Well, we can learn something about the low X gluon PDF. If the PDF is 20 times larger, we should, roughly speaking, see 20 times more neutrinos from charm. So we can rule out this hypothesis. Only with the data we have, we can put the sort of upper limit here. Okay, why is that interesting? One example is gluon saturation at very low X. We have a lot of gluons, and typically what we do is we just split gluons. So gluons can radiate off other gluons, but once the density becomes super large, the opposite can happen too. Two gluons can find and recombine into one gluon. So that will stop the rise of the gluon PDF and therefore, well, change the number of gluons and therefore change the number of neutrinos. And this is well, roughly the region where we start or expect to see this in protons, and we're actually in the region where we expect that this starts to play a role. So that's interesting. So this is just one example. You could also think about, if for the high X side, if you believe in intrinsic charm, well, so if you have charm quarks in the PDFs that carry a large momentum fraction as predicted by some models, then that should also lead to more neutrinos that we could see. Okay, so these are some fundamental QCD physics examples of what we could probe. Now, as promised, there's something for the astro-particle physicists too. They are also interested in this. There are sort of two applications. So if you come from cosmic ray physics like Pierre Auger, then many people talk about the cosmic ray muon puzzle that's really bothering them. So they have simulations of hadronic interactions for pion and kaon production, for example. And so these are really like super high energy cosmic rays at the highest energies we have, hitting the atmosphere, producing enormous air showers that whose properties we measure. And one of the things we measure is how many muons come out at the bottom. And we see too many muons, actually 8 sigma too many muons compared to our modeling. So that's a problem because, well, how can we properly analyze the data if our simulation doesn't describe it? And what do we want to measure in the end? We want to measure the composition of cosmic rays and then deduct their origin. But if you would use these simulations, some of them would tell you that, well, all the cosmic rays are made of uranium. That doesn't really make sense, yeah?
What's 8 sigma like in percentages?
Well, it's between here and here, but yeah, good question. Well, I can tell you what it would mean for our neutrino fluxes in the moment. Okay. I mean, I don't think it's a super huge difference, but it's order one-ish. Let's say order one. That's probably not wrong, but so not order of magnitude, it's order one. But yeah, so the problem is that yeah, we can't really infer the nature of the projectile, so of the cosmic ray. So we can't really do the physics we would really like to do with it. So then this is like a 10, 20-year-old story, and people thought about what could it be, and they really analyzed a lot of details and said that, okay, one of our hypotheses, we all think that it's some modeling of soft QCD physics, which is really problematic because we can't use Feynman diagrams to calculate it. It's all some more modeling. So, okay, not too surprising that something is slightly off there. I mean, a lot of it is tuned to data, but how can you tune to data if there is no data at these super high energies? So it wasn't really a big surprise that we are a bit off. But then people came up with some changes. So for example, what you would really like to do is have less pi zeros, so less electromagnetic shower, have more hadronic shower. And one thing you would like to or could do is increase your fraction of kaons. Okay. That actually seems to work. So this is the Pierre Auger measurement. And if we, so this is our baseline, and if we increase the fraction of kaons, this is a model that I have worked on with Luis Ancordoki, then we could resolve this discrepancy. How would it, the simplest scenario looks at FASER? Well, I mean, our neutrinos come from pions and kaons. So if we have a little bit less pions, a little bit more kaons, then to fix this anomaly would actually end up with a lot more kaons, like a factor 2 more kaons or something like this. And our energy spectrum or our number of electron neutrinos would change significantly. This is a bit of an extreme example that I chose because it's easy to illustrate on a slide. Of course, there are many subtleties that one can reduce this effect, but I think the point is clear. We can test forward pion-kaon production that is useful to investigate the nature of the cosmic ray muon puzzle. Charm production, well, if I ask my IceCube colleagues how they call forward charm production, they call it their prompt atmospheric neutrino flux background. So neutrinos that are produced in charm decays. And this hasn't really been measured yet. To use the words of Francis Halsen, he said, well, we don't have any data, we don't have a good theory either. So if you can give us some data, then we can start to build a better theory and make better predictions. This is just like this light orange here is our current sort of PDF uncertainties and how they propagate to the prompt neutrino flux. And then this is some projections on how one could then constrain them and the impact on the neutrino flux. And you can see that the impact is enormous. So we can really constrain one of the main uncertainties that go in there, the PDF uncertainties. It makes these predictions better, reduce uncertainties for the astrophysical neutrino searches, and therefore increase the sort of ability to do astro-particle physics with them. Okay, so I hope I convinced you that there is an interested user community, that this is actually quite some nice analogies between LHC physics, where we have collisions in the sort of center of mass frame, and cosmic ray physics, where we have the same collisions just in the fixed target frame. Okay, so I'm not sure how much time I have. I have a little bit left. Okay, so I just wanted to show you what we could do with measurements of interactions. So I kind of showed that before, like electron muon tau neutrinos, but then now in terms of the interaction cross-section, or here interaction cross-section over energy as a function of energy. Shown in gray is existing measurements, and there were some at accelerator experiments, for example, at Fermilab. IceCube has some measurements too, but well, here there is still a gap, and for electron tau neutrinos, there are really no high energy measurements, so we'd like to measure it, just to see if our models work out. And this is a sort of projection on how well this could be measured from, I think, this paper here. And if we measure them all together, especially the tau neutrinos, then we can also test if the cross-sections are the same as predicted, or if there is some violation of lepton flavor universality or not. Actually, we started doing this. So these are the both from this margin analysis in blue, and then the muon appearance analysis in red. First measurements of the cross-section for antineutrinos here, neutrinos here. And yeah, you can see that the uncertainties are still large, statistics limited at the moment, but they are roughly where they should be. So these are the first measurements of cross-sections in this regime. Of course, these measurements will get way more precise, especially with the Future Forward Physics facility. I mean, the fluxes go up by a few orders of magnitude, and then the statistical precision goes down a lot. Well, what can we do with, like, beyond the total cross-section? What else could we do? Well, I mean, we have neutrinos, TeV energy neutrinos colliding with a detector. The detector, in our case, consists of tungsten. So it's essentially a neutrino-ion collider at the same center of mass energy as the electron-ion collider. That's why I called it a neutrino-ion collider. So one can do the same sort of physics, but with charge current interactions instead of neutral current interactions. So one can look for probe PDFs. So for example, nuclear PDFs, EMC effect, shattering, something like this. One has some additional flavor sensitivity. So for example, you have neutrinos, strange, goes to lepton plus a charm. Charm can be identified in the margin detectors. So you can measure the strangeness content of the proton in a way that you couldn't do with neutral current interactions. There are also some other effects. So, for example, how does hadronization inside the nuclear medium or parton showers inside the nuclear medium develop? I always try to find someone to explain this to me, but I wasn't successful yet. I'm not sure if there is even someone who thought about it or solved it. It's mentioned as a physics case of the EIC, but we could also probe this with neutrino interactions. Okay. For the PDFs, this was actually studied by Cruz Martinez et al. That made some projections. Therefore, one can actually constrain the PDFs quite a bit. So for the light quarks, for the valence quarks, by about a factor of 2, and for the strange quark, even more. And why is that interesting? Well, I mean, PDFs are the input for any of our main collider physics predictions, like Atlas CMS, Higgs boson production, weak boson production, and one can lower the uncertainties associated with it, and therefore improves the measurements of the couplings, of the W mass, or whatever needs these PDFs. So it's of great interest also for the main LHC community. Or people also start to think about the degeneracy between PDFs and new physics effects. So for example, in terms of an EFT. These typically, new physics EFT operators typically predict mild changes in the some distribution, some kinematic distribution, typically at some high energies, so some not so well probed kinematic region. And how can we make sure that we don't absorb these changes into our PDFs, for example? Could we just fit away the new physics? That's a real concern. And one way to address this is to break the degeneracy with complementary data. So, for example, with these low energy experiments, like neutrino experiments or even the EIC. Okay. Here I have one slide because it was done by a person here from Unicamp, who unfortunately isn't here, I've been told, but so this is actually using the tau neutrinos, and for tau neutrinos, if you calculate the structure functions or the cross section, you see that while there are terms proportional to all the structure functions F1, F2, F3, but also F4 and F5. So these are typically ignored. They are proportional to the lepton mass, and so they don't really play a role. But for tau neutrino, well, tau mass is much more sizable. So we can actually start to measure F4 and F5, which hasn't been done before, as far as I know. And here they made some predictions on how the total cross section would change. And here is with and without the F5. And here are some kinematic distributions for, I think, a pion from tau decay. And we can see that, a large sample of tau neutrinos would allow us for the first time to really measure this F4 and F5. And check with our textbook predictions. Okay, there's also plenty of new physics that one can do, and I just say it here. So one could introduce new particles that, for whatever reason, like to decay into neutrinos, like tau neutrinos especially. One can look at stereo neutrino oscillations, so see this as a short baseline neutrino experiment. Some people look for magnetic or electromagnetic properties of neutrinos, like a magnetic moment or charge radius, or non-standard interactions of neutrinos that one could probe, in particular with tau neutrinos. And there are also some more exotic models on new particles that could be produced in neutrino interactions that only couple to neutrinos. These are just a few examples. I'm sure there are more, but yeah, if you're interested in that, let me know. So let me conclude. Before I show my summary slide, I just wanted to show this one here. This is the muon neutrino flux at different experiments. So the black here is existing ones, blue is FASER at the FBF, Dune would be up here. And then there are also some other new proposed colliders like the FCC or the muon collider. And you can see that both of them would actually have if we would put something like FASER there, would be able to observe huge numbers of neutrinos. I mean, these are really like enormous numbers. So for muon collider, because muons decay to neutrinos, for FCC, well, there's just a huge luminosity and yeah, huge number of particles produced. So this is something we should already at the beginning sort of think about if we consider these machines. So actually the muon collider would give us a real neutrino ion collider that is not at all statistics limited, where we can really do all sorts of multi-differential measurements without work. I mean, we have a kilohertz rate of neutrinos, so that would be super amazing. Okay, so it's also something to keep in mind for the future if we ever build one of those machines. So let me conclude. I've shown you that a new novel program emerged that looks at forward physics at the LHC. And it already has its first successes. So as I've shown, FASER observed collider neutrinos, or neutrinos produced at colliders, for the first time in over 50 years of hadron collider physics. And this is a term that one of my colleagues used. We enter an era of multi-messenger collider physics, with neutrinos being a messenger to QCD, or the new particles maybe being a messenger to the dark sector. Of course, that's making the connection to multi-messenger astronomy. I'm sure there are more results to come. Here I just summarize all the bunch of buzzwords that what we are doing and how it connects to what various communities are interesting in, from astro-particle, dark matter, new particles, neutrinos, and QCD. As a phenomenologist or theorist, I can say that this has always played an important role in this program, and I think it will continue to play one. If you're interested in contributing one way or another, if you have a good idea, and we had some discussion earlier where we might have had a good idea on what else we could do, then let me know. Yeah, new ideas are always welcome. And so thank you for listening.
When si introduce the dark photo, the part in the top, not much easy to produce by the pipe with the imagined decay. We have the final electron, and this final electron can emit a dark photo. Or this is too low.
Like sort of as a final state radiation. Yeah. I think, well, you would have that in like, let's say, charged pion decay, I guess. Mm-hmm. So then you have a muon could radiate it off. Good question. It's probably possible. I mean, the neutral pions have the advantage that every neutral pion decays, but charged pions have the disadvantage that 99.9% of them interact or get absorbed before they decay. So you sort of lose there because you only have a subset of them, or charm production, you have much less charm than you have pions. So that's why pion decay, if possible, always dominates. That's my experience. But there are other examples, like my colleagues looked at the muon-philic particle to explain G-2, and this is actually the main production mode, final state radiation of a muon. Somewhat constructed, perhaps, but yeah, a good example, I would say.
You mentioned the neutrino.
Yeah.
I mean, what is the, from what I understood, according to the standard model, it's
yeah, so in this, I mean, in the standard model, it's super low, below any hope of measuring it. There were some models, typically from the early 90s, where people considered that as an explanation for neutrino oscillation. So rather ancient models, there were some exotic versions of supersymmetry where you somehow could get a high magnetic moment. I'm not sure. I wouldn't say that these are really the models I would bet my money on, let's say it this way. But people proposed it, but yeah, it's also, I would say, perhaps not the best example. The charge radius is a more interesting one. So the charge radius is something that, I mean, it's essentially the diagram with a W loop that, like the penguin diagram with a W loop that emits a photon. They gave it a fancy name, charge radius. But that's actually something where we are pretty close already to the standard model prediction. And with the full statistics of the forward physics facility, assuming we can control all the various systematics that go in, one may be able to observe or measure the standard model value for the first time. Oh, yeah. Let's see. So what's this here? So this is so you have neutrino, W loop, and then the photon interacting with, let's say, some nucleus. So it's
yeah, but isn't the magnetic moment basically some kind of not Fourier harmonic decomposition of charge radius?
Let's see. I mean, in the end, if you write down the form factor for the neutrino photon one, and the charge radius, the charge, the magnetic moment are just the different expansion parameters in this expansion. And this diagram would contribute 0 to the neutrino charge and something to the charge radius. And I don't think it contributes to the magnetic moment, but probably for some symmetry argument that I forgot, which can probably work through. But yeah. So this is something we, of course, expect to see, but this will contribute to neutral current scattering. And the effect would really be super tiny. So this would be a real precision measurement that would require lots of control over everything. But
FASER can measure this?
We would need the full forward physics facility, so the full statistics of these millions of neutrinos. So FASER alone is still too small.
More questions?
Yeah.
I think probably the rate is very small, but when you measure the solar atmospheric fields,
So say again?
The solar atmospheric fields are producing effects cosmic rays hitting the sun and can you use this because it's very, very high energy. But I think probably the flux is very small because you are a small detector.
Yeah. I mean, the detector is roughly 1 ton. So I suspect that, any source besides the LHC is, which has a great advantage of having an intense beam directly directed at the detector, will be hopeless. So, I mean, if there should be a sizable flux, we would have probably seen it in, I don't know, hyper K or super K or something like this, which is orders of magnitude larger.
Out of curiosity, the emotions that you had in this boxes, were they stacked horizontally or vertically? Do you know that? Oh,
they are vertically, yeah. So the beam comes from the side, and then you have layer of emulsion, tungsten, and so on.
But I just was wondering because the angle is very, very small.
Yeah.
So they could actually, you could see the part also in the horizontal. That's what I was wondering. But,
in principle, yes. Vertically, because then you can connect the dots between the different.
The trajectories.
Yeah.
Thank you.
These hadrons, where do they decay? Inside the atom?
Well, it depends. So a jump quark decays more or less promptly, right? The lifetime is something like a few millimeters, something like this. So they decay essentially right there. Pions have well, C tau is about 10 meters. So C tau times boost factors is probably something in the multi-kilometer range. So most of them don't even decay, they just get deflected and hit an absorber or something like this, but then some of them will decay. Roughly speaking, I don't think I have a figure, but so the first absorber is about 20 meters after Atlas, and then afterwards quadrupole magnets start, so they focus a beam. So roughly speaking, they have 20 meters to decay, but that's still a sizable length, so enough to get yeah, our neutrinos. And I would say most neutrinos come from within 20 meters of Atlas, probably something like 90% or so, because then they very quickly get deflected, and once they get deflected, they don't point at us anymore. So, yeah.
Further questions? If not, let's say